In this section, we're going to talk mainly about finding groups of similar items. So in the first video here, we're going to focus largely on generating synthetic datasets with scikit-lern. Let's move right in. So I'm back in my Jupyter notebook with Chapter 6 notebook open. So this again is in the accompanying code files that comes with this course. And so I want to talk firstly a little bit about why somebody would want to generate synthetic datasets. The main reason is when we take real-world datasets, we don't really know what is the underlying rule that governs the dataset, right? So to give you a very simple example, let's say we are predicting tree species based on how tall they are, right? And to be extremely precise, the species and its height is governed by a lot of factors occurring in nature, in biology, and in other natural sciences. And it's not as simple as we have a coefficient on a linear model and we say the species dictates the height in this sort of relationship, right? So anything you do in modeling or machine learning is simply sort of creating a simplified version expressed in a mathematical way of reality, right? So that's all well and good, and that's ultimately what everybody wants, the practical choice. But when we need to understand how powerful models are, or what kind of outcomes or what kind of performance a model has, we need to bear in mind that leveraging a synthetic dataset may help us understand and recover how different datasets interact with different models. Which all sounds very theoretical, but the golden rule is this. If you have a dataset that is generated by a linear model, another linear model should be able to perfectly recover the coefficients of the linear model that is generating the data, right? So this is why synthetic datasets make sense. We can make synthetic datasets knowing full well what the perfect answer is and see whether the model can recover the perfect answer. And that allows us to understand how the model performs in different situations. And so when we actually roll these models out to real-world data, it gives us a better handle on what sources of error might happen and where might be the gap between reality and performance. So here in Chapter 6, let's kick off by first importing pandas. So in in1 we do import pandas as PD. And then in in2 I'm showing you guys a not very often used module within pandas, which is Pandas Testing. So in in2 we import pandas.utilities.testing as TM. In in3 we can specify how many rows and columns or otherwise data points and features we want to generate from pandas using this testing module. And that helps us sort of create different situations on how much data we have and how many features these data have, right? So here we're specifying that we want 15 rows or otherwise 15 data points and 3 columns or otherwise 3 features. Again, with anything random or generative, we want to set a seed so that we can reproduce this result. So here I am importing numpy as np, and then I'm setting the random seed to be 444 by calling np.random.seed. And so here in in6, this is the first function I'm going to show you. So the first function is makeTimeDataFrame, specifying the frequency being d, which is daily. And so what this means is it gives us 3 columns and 15 rows of a time series data spaced out daily. As you can see in out6, on the left-hand side, leftmost column, it's the time-based index, and the time-based index increments once every day. And we have 3 variables that vary between what looks like -3 and +3. So I think this is just a Gaussian distributed random variable that gets sampled in A, B, and C. So in in8, we're looking at a different function. So we have tm.makeDataFrame. And this simply gives us a dummy data frame that again has values generated randomly or sampled randomly from a Gaussian distribution, with the leftmost indices being random strings that we can use to identify the row. In in10, we can verify that makeDataFrame actually corresponds to the n and the k that was specified up there, where we create 15 data points or 15 rows and 3 features or 3 columns, right? So obviously we don't only have make time data frame and make data frame. We actually have a lot of other stuff. So to properly scope out what this module can do, we can use the directory function dir, and we basically use a list comprehension in ins11 to scope out all the functions that we can use to create dummy data. So here we can see that we can make custom data frames, we can make date indexes, we can make interval indexes, we can make missing custom data frame, we can make panels, and so on and so forth. And this, I strongly encourage you to explore on your own time. So the other function I want to show you is from scikit-lern. So in sklearn.datasets, there's a make classification function. And basically what this does, it creates clusters of points normally distributed around vertices of an n-informative dimensional hypercube of size length 2 times class separation. So what that really means is we're creating clusters of points normally distributed around some points in a space, and it basically creates this space or this area that contains these points based on the class separation parameter. And so what that really means is we create a few clusters, we create it in a few informative feature spaces, and we create the features that may be equal or larger than the number of informative features. So here you can see that number of features is 20, and number of informative features is actually just 2. So within the 20 features, only 2 of them are relevant. And we're generating 100 samples for this classification problem. We're generating 2 classes, and we have 2 clusters per class. And so with the class separation being at 1.0, it means that the classification data is generated over 2 dimensions, but 20 features are present, and the classes are not very separated, so it's harder for a classifier to separate them. And as you can see here, the make classification creates x and y as our convention. Input is x, output is y, and you can see that the x shape is what we expect, and also the contents is also what we expect, and so is y shape and y. So that's all there is to generating dummy data sets.